We're almost at the end of the reactions that we need to know for organic chemistry. Now, the last reactions are substitution reactions. Substitution. Now, what is a substitute? Substitution reaction. Okay. A substitute is you take a player off and put somebody else on. In other words, we are going to replace something. We're going to replace something in a reaction. Okay. So we're going to look, and this is going to be in my schedule 5A, is an alkane plus a halogen. These are the ones you got to know. An alkane plus a halogen. All right. What does it give? Well, it gives a halo alkane, okay, plus a hydrogen halide. An alkane plus a halogen. Let's just take one simply. CC, okay, I know we use this one, but it just makes sense to do this. Okay, there we go. All right, and we're going to take an alkane, there it is, okay, and we're going to put a halogen, which is essentially, in this case, Br2, I2, F2, or we could put in Cl2. The halogen is the gas form. Remember, it's the diatomic one. Okay, we're going to form a halo alkane, which means we're going to put a halogen on, and we're going to be left with a hydrogen halo. So what happens over here? All right, let's look at the reaction mechanics. Well, first of all, this Br2, any one of these is going to split into a Br minus plus another Br minus. All right, and what happens over here then is I say, all right, this changes, and I'm going to end up with, I've got my same there. Now I say, right, I'm going to take a hydrogen from here and remove it, and I'm going to put the Br there. All right, so let's just go back and we say red, we remove the hydrogen, okay, and there is my substitute. All right, so what happens to the remaining one? That becomes my HBr. This one was left over. And here's my halo alkane is there. And my halo alkane in this case is going to look like this. Right? So I've got a C like that. All right, and I put in a Br there. Okay. And that one is going to be, it's 1-bromo-methethane is my halo alkane. So a substitution in this case, I'm putting a halogen gas in there, and I'm replacing on the alkane, I'm substituting the H with the Br. And that H goes and links up with the remaining Br molecule that's left over. Okay. Now, this one here, and this is what you have to remember, and you'll see why when we do examples, NB, this needs UV, heat, and sunlight, or UV light. Okay? So when they tell us they're going to give us reactions, and they're going to tell us this happens in the presence of ultraviolet light. The moment you see that, you know that it's going to be this substitution reaction over here. That was 5A. Now 5B is another substitution reaction. Okay? 5B is another substitution. It's an alcohol. 5B is an alcohol plus a hydrogen halide. Hydrogen halide. And I get out a halo alkane plus water. So let's put a simple alcohol. Well, no, hang on. Before we start this, we've got to decide. We have got primary, secondary, and tertiary, right? Primary, secondary, and tertiary alcohol. Okay, that we've got to deal with. They're not all the same. They are different. So let us first look at a tertiary alcohol, right? The same process occurs, tertiary alcohol. Okay, let's take this one over here. And there's our ol, okay? And we've got this. Why is this a tertiary? Because it's attached to, there's the primary, or rather, there's the simplest, the C and the OH. And it's linked to 1, 2, 3. If it was linked to 1, okay, primary, 2, secondary, tertiary like that. Okay, I'm just going to complete all my H's here. The thing that I get wrong time after time. Okay, now, I am going to say this is this. Now I'm going to add a hydrogen halide. I used HCl. So first of all, this is an acid. It's going to ionize in the water, isn't it? Or into the alcohol over here. All right. And what am I going to end up with? Well, a haloalkane and water. Well, first of all, we know that if we want to form water, we have to find an OH and an H, don't we? Right? So we say, okay, now we've been through this process before. Okay. We have been through this process before where we say, right, hang on, there's an OH. So we've immediately we know that our, okay, C like that, okay, this OH is going to be removed. Okay, in the spirit of what's removed, the OH removed. Right? The OH is removed. Right. And then I need a hydrogen. Okay? So I say, right, the hydrogen comes from this guy here. Okay? So that's been used up. Remember, we've got to use up everything we've got. So what happens, what's left, is that the chlorine, blue, the chlorine, this guy here, goes and sits in that space, over there like that. So we end up with this. Okay? We end up with this one over here. Okay, C, okay. There are hydrogens around all of those, Cl like that. Remember, that came into the red space. And my water is on the other side. H2O. All right, like that. And what is this? This is, well, what do? We find the longest chain. Okay, just take that guy there. And that longest chain is then a what? 1, 2, 3 meth eth prop, single bonds. So it is a propane. But on the propane, what have we got? Let me just move this because it gets long in front. So on the propane, we say, let's number it. 1, 2, 3. Okay, blank. So we say, right, that is a propane. On it, it's 2-chloro. Let me do it according to my thingy. So now we go with our blue pen, remember, and we go sides. Okay, sides on 2, there's a chloro. On 2, there's a methyl. So therefore, I now put them in order, and I say it's always the halide first. So it's 2-chloro, 2-methyl propane. Okie dokes. There we go. Now, that is if we are using a oops, just take this back down. If we're using a tertiary alcohol, but now what happens if we've got primary and secondary alcohols? Let's look at an example with a primary and secondary alcohol. Okay. What do we do? The same process takes place. Okay. Whoop, I need to just go back. Sorry, guys, my bad. I need to go back here. This reaction, let me put it here. All right. With a tertiary alcohol is, and let's just look and put it in red. This is at room temperature, and it's quite quick. Okay. All right. All right. It's quite a simple, quick reaction to take place. Yeah, which makes you think this next one is not. No, it's not. All right. The next one, okay, primary, secondary alcohols. We say the same process takes place, but we need heat. I'm going to put in here, all right, heat over there. All right. Heat. All right. Just put that out the way. Heated, and it's slow. And it's slow. All right? Okay, for the reaction, we don't use the hydrogen halide. We generally use a solid halide. Remember, the halide is the F minus, Cl minus, I minus. It's the ion, right? And the, sorry, I've got him. Fluorine, chlorine, bromine, iodine. Okay, I've got them all that I need. 1, 2, 3, 4, yeah. Those are my halides, right? There they are. Okay. We generally use it. So I'm going to use this one here. I'm going to use methanol. COH. I'm just using the smaller ones like so. All right. Plus, and we use the solid halide NaBr plus H2SO4. Okay. No, we don't use HCl because it could mess it up with the chlorine going and landing on there, right? Okay. So what happens here? Now I'm going to go through this fairly quickly. So we need to form, okay, water is going to come off it, right? We know that it's a haloalkane and water. So once again, yes, we get the removal of the OH. Remember, I put that in red. Okay. The OH has gone. OH removed. Okay. Then we need to, but now we've got NaBr and H2SO4. Where do I get my hydrogen from? Well, what happens to an acid? This gives off the H plus, and it leaves me with HSO4 minus. All right. This goes to ionize Na plus Br. Sorry, dissociate. That dissociates. The acid ionizes into that. I think you can see where this is going now. So we say, all right, hold on. Into the red slot is my Br. Right? Goes in there. The sodium, okay, my H plus that's going to link to form the water comes from the acid, like that. So this is from the acid. All right? It's a diprotic acid. 2 protons are coming across from there to there. Then the next part is I say, right, well, what happens to the remaining guys? Let's see. Oh, let's call them blue. Okay, what happens to those two? Well, they get together and they form a salt. NaHSO4. Okay? And that is sodium bisulfate. Sorry. Okay? Because that's plus and that's a minus 1. They form together like that. So that forms a salt like that. As I say, I went through that one fairly quickly because it's not prevalent in many or in detail in many of the textbooks that I have seen and that I've used to compile this. Okay. The next one is also not in many textbooks, but I am going to do it anyway. Okay, it's in one. It's a it's a haloalkane. Okay, haloalkane plus a base. Okay, and it goes to an alcohol, okay, plus a salt. Okay, so the textbook I said get a hydrogen thing, but that's not to completion. That's not what I was able to come up in the research I did. But let's just do it anyway. Let's form a halo alkane, and we've got here, okay, a Cl, all right, okay, like this, H, okay, like so, sorry, it's been, okay, so what have I got here? I have got a meth eth prop, okay, it's a propane, so this is going to be 1 chloro propane. And let's put a base NaOH. Okay. Now we know that splits into Na plus an OH minus. Why? Well, we know that acids do and bases both do, don't they? When we put them in, they ionize. Okay. And we need to form an alcohol. Well, already the alcohol bit needs the OH. So you can bet your bottom dollar that the alcohol is going to form with the OH, right? So you can see here, it's pretty straightforward. Form the alcohol first, okay? And first of all, we cut off the Cl. So now what have we got left? We've got a Cl minus, and we've got that. Yep, and then the green bit, the OH, goes and sits on there. Okay, let me complete my drawing here. Okay, now you can see we've formed the alcohol. Okay, and what is left? Well, it's pretty obvious, isn't it? The sodium links up with that to form the salt. So we've taken 1 chloropropane to propanol, right? Propanol. Like so. This portion here, all right, and just generally, wherever we see the following: heated under reflux. What does this mean? Okay, it means it's heated with a condenser vertically above it. What is a condenser? Well, what is condensation? Condensation is when something changes from a gas to a liquid. So what we do is we have, oh, sorry, that's not what I wanted to do. Okay, I wanted to actually just have a place to make a drawing here. All right. It's heated under reflux. Essentially, guys, it looks like this. We've got our beaker over here. All right. Okay, let's put our beaker there like so, and just try and get it tidy. And inside here, I'm going to put in our mixture. This is our mixture here. All right. On top of the beaker over here, we have got something that looks like this. All right. It's taken up like that, and then right up top there, that is a long tube at the top, right? This is sealed on the sides, so that's all sealed up. So it's a closed container, all right? And around the outside of this thing, okay, I'll draw it in green. Around the outside of it is another tube, glass tube, sealed with an inlet there and an out. And into here, okay, we pump cold water. All right? So we're getting inside here, we get condensation. If any of you have ever done it, you get Liebig's-Condenser, which is where basically you boil water here and you can, what drips out the other end, it's to produce distilled water. This is so that all of the gases become drops and fall back in. And why do we do this? Because essentially you're forming an alcohol. And an alcohol under heat is going to do what? It's going to evaporate. So you don't want to lose. This is to retain the volatiles. And volatiles are the gases that will essentially evaporate. Okay? And you don't want it to evaporate. Why don't we want it to evaporate? Because we are actually, why not? Because we are producing an alcohol. Okay, and its boiling point is low. So therefore, you want to make sure that you retain it. Otherwise, you're going to lose the whole lot. Just some people have asked me, okay, please, what is this? A Lindsay Catalyst. Okay, a Lindsay Catalyst. Do you remember when we did the addition reaction, we changed an ene to an ane? Remember? By adding something in and breaking the bonds. Well, you can also change an ine to an ene. And obviously then it will continue to an ane. But if you wanted to stop at that point only, you use the Lindsay Catalyst. So this is, okay, auto-saving, to change an alkyne to an alkene and no further reduction to an alkane. So it's changing an alkyne to an alkene and stopping there, not going further to get an alkane. All right? What is it made of? It's made of palladium, which is put onto a strip of calcium carbonate, CaCO3, CaCO3, calcium carbonate, all right? Then when we've done this, this is put onto it. Then when we've done that, afterwards, after we poison with lead or sulfur. Okay? That's what we do with these. That's what we've got here with this. Okay? That's a Lindsay catalyst. Okay? The next stage is what I want to go through now, is I want to talk about reactions of alkynes. Okay? I'll quickly deal, you have to know these, all right? Markovnikov's rule. Okay? You might want to look these up. Markovnikov's rule. Okay? And Zaitsev's rule. Okay? Just look up those guys there. Markovnikov, it says in an addition of a protic acid, protic, HCl, HBrHI, in other words, a hydrogen halide, to an alkene or an alkyne, the H plus ion bonds to the carbon atom with the greatest number of hydrogen atoms in the starting alkene or alkyne. Okay? Zaitsev's rule, it predicts the favored alkene in an elimination reaction. It said the most substituted product will be the most stable. All right? Let's have a look at Zaitsev's rule. I've got one here if you want one. We've got here, okay, let's have a look at this. We've got this guy here. 1, 2, 4. Okay, and we've got this. Oh. Okay, we've got this here, and we've got, no, that's iodine on top there. Iodine on top, like so. And I'm not going to put all the hydrogens in because it's time. And we put in KOH over there like that, right? So basically what we're doing is we're putting an okay, and now what I'm going to do here is I'm going to put the OH, okay? We are taking this, all right, our upper step. Let's label it and number it. So first of all, we label 1, 2, 3, 4. Why? Because the iodine is the closest to that end. I can't label it 3-iodo. So it's going to be 2-iodo, okay, 2-iodo, and it's meth, eth, prop, butane, plus a strong base, K and OH. I've just basically ionized it straight away, okay? So now, under these conditions, okay, what are we saying? We're saying here the iodine, all right, this is an elimination reaction, so the iodine is going to be chopped off, okay? Okay, so basically like that, correct? Okay, I've got the iodine. So the space was made over there. Okay, the space was made and we made it in red as usual. So now the iodine is gone. Okay, this has now been removed. All right. Then it says that the most substituted product will be the most stable. All right. Okay, in other words, it prefers to swing to the least number of hydrogen atoms. Have a look here. We know that this is going to form a double bond now. Okay, this is an elimination reaction, which means we're going from an ane to an ene. Elimination, addition, ene to ane, elimination, we're taking something away, so we're going from an ane back to an ene, all right? So what we're saying here is, which way is this going to swing? Okay, it swings according to Zaitsev's rule. It swings to the carbon with the least number of hydrogen, least number of H atoms. So it will prefer, this electron here now will prefer to go that way. Okay, maybe it could have gone the other way. Right? So it prefers to form this. It prefers to form that one. Like so. Okay, this is preferred. Cool. According to Zaitsev's rule. Okay, it prefers to form that, so it's going to form, generally speaking, okay, what is this? Okay, it's an ene. We say we're going through our family. It's an ene because a double bond, meth, eth, prop, bute, and it's going to be bute 2-ene is what's going to be produced generally. That's what we prefer to produce, all right? The secondary one that will be produced would be butene 1-butene, all right? This is called the major product. The major product, okay? And the minor product, okay? The minor product is going to be 1-butene, which would be this one here. Okay, like that. 1, 2, see, I've done it again. Please excuse me where I've made those mistakes. I do them too quickly, okay, because I'm trying to get through it. So please forgive me where you see those and just rub them out. 1, 2, 3, and a fourth, right? So in other words, this is straightforward butene 1-butene or but 1-ene. And what have we got? This is the minor product. This one here is the preferred one. Okay? Because it will swing, according to Zaitsev's rule, it swings that way. All right? Major, minor, the same is going to go with an alcohol depending upon where you remove the OH. Please remember that. If the OH is removed from the middle somewhere, it's going to, you're going to swing to the one with the least number of hydrogen atoms. Okay, right. The last part we've got to look at here is alkynes. Okay, now the alkynes, I'm going to go through it fairly quickly. Okay, so reaction of alkynes. Of alkynes, all right? Now the alkynes, let's take ethyne. So meth, eth, okay? And basically we've got an H and an H on that side. So that's ethyne. Okay, now what are we going to do? Let's add a to this, and this is halogenation. I'm going to do halogenation, which is an addition. So that means break bonds. Right? So the first step of this is I'm going to have an H, a C, a double bond C. I think you're getting the, whoops. See, there goes Kevin again with his over-eagerness. Okay. And putting them in everywhere. Can you see what we've got here? Okay. Look, we took this bond over here. Let me just put it in green. I took this guy and I broke it. So when I break it, I must put him up top there, right? And there he is. That bond is now broken over there. So that is going to take, because this is going to split into an F plus, F plus in your dreams, okay, F minus, and that's going to split into an F minus. That goes there, and we get, okay. So the first one we get is we're going to get, well, let's name it, come on, okay, let's name it, right? We've got, this is ethene now. Isn't it? We've taken an ine, step 1, goes down to an ene, okay? Remember, the Lindsay Catalyst would come in here, right? The Lindsay Catalyst, if you wanted to stop there, okay? But there is a next step down. The next step is now we're going to take it to an ane. So this is an ethene, meth eth, and it's 1, 2, fluoroethene, isn't it? Now we're going to add another F2 to this guy here. Okay, what do you think is going to happen now? Well, it's going to break the remaining bond. So I've got an H there. This is my C, okay, and this is my H over here. Now I'm going to keep the green one as it was. Keep the green. Remember, there's the F and the F from the first bond. Okay, there's that one broken. Now I'm going to go red, whoops, blue, it doesn't matter, and I'm going to break that bond, okay? And that's going to, this F2 goes to an F minus and another F minus, correct? So look at these two go there, F and an F. So this has now gone us to, well, this is now an ethane, isn't it? And it's what? Sides. We've got on 1 and 2. So we've got 1, 1, 2, 2, tetraethane. Tetra, fluoro, ethane. Tetra is 4. There's 4 fluoros, and where are they connected? 1 on 1, 1 on 1, 1 on 2, and 1 on 2. Okay? Tetrafluoroethane. Okay? The next piece of this is going to be where we say, okay, what about combustion? Combustion of an ine. Okay? Combustion of an ine, it does exactly the same. This over here as an ane, with an H, okay, with an H, plus O2 always gives us CO2 plus H2O. It's the same as an alcohol burning, or an alkene, or an alkane burning. Okay, combustion is burning, right? All right. Now, just the last bit. Remember here, you've got 3 bonds. The 3 bonds, the bond energy of a CC is equal to 347 kilojoules per mole. A CCC is 614. Okay? And a C triple bond C is equal to 839. Okay? Now, if you go and you basically just take them apart, 347, all right, and 614, okay, 614 not divide, 614 minus 347, okay, 614 minus 347 is equal to 267. So it's 267 kilojoules per mole is the second bond. The third bond, all right, is going to be 839 minus 614 is 225. So it's 347 kilojoules per mole for that one, kilojoules per mole. This is the energy to break the bond. Energy to break the bond. Okay? So what have I got here? Can you see the energy to break the first of the triple? There you've got your 3. So to break that one, the first one of the 3 bonds, okay, to break that is only 225. To break the second one is 267. To break the third is 347 kilojoules per mole. So the more bonds, the less energy at the top level, the first one, or at level 3, the less energy is needed to break it. Okay, that brings us generally to the end of organic chemistry. I do apologize for going over, but I wanted to just finish this section. Okay, this is from a lot of input from different students asking about how does this work, how does that work. I hope I've covered it. As I've said, if there are some hydrogen stripes where I've added in too many, I've tried to put the names at the end so that we can just go back and look at those. My bad if I have done any. Okay, thank you for watching, and I hope that organic chemistry is fun. Cheers, bye.